It's exam 3 for physics 101, fall 25. First, start with this. A cart has a speed of 2 meters per second at point A, and it goes down the slope, and I give you the distance at point B, and I want to know the speed at point B and the speed at point C. First, recognize that I have kinetic energy and I have potential energy here. Likewise, I have both here. But down here I have no potential energy, I only have kinetic energy. I know each of these, so I can let that be my reference point and then just set it equal to the energy at points B and C. So this should say speed right here, by the way. Or velocity is fine, but there's really not a direction. Anyway, or not that we know anyway. What is the speed at point B? So I say the kinetic energy plus the potential energy, that's 1/2 mv, I'm going to call this VA squared plus mgha is equal to, and then notice that the masses, I can divide through by m through each term, and since it's in every term, that goes away. So I have a 1/2 of 2 squared plus 10 times 10. That's 10, that's the g, 10 meters per second squared, equals 1/2 times VB squared, that's what I want to know, plus 10 times 8. So that's equal to 1/2 of 4. 102 minus 80 times 2 square root of all of that gives me VB, and that's equal to, yeah, that's equal to the square root of 44, which is 6.6 meters per second. And then for the second one, the velocity at point C, this one's a little easier actually. So I can actually start right here because I'm this whole left-hand side of the equation is the same. So I'm just going to write that number. That's 1/2 of 4, which is 2. That's 102 equals 1/2 of VC squared. Notice what I did there. I did a little bit differently. I'm just going to alter this equation right here by getting rid of that term and making that into a C, and then that becomes the equation for part B. Because there is no potential energy at point C, that term goes away, and then I just change the speed. The left-hand side stays the same. And so that's VC is the square root of 204, and that's equal to 14 meters per second. Okay? So there's this block, it's initially at rest, so it only has potential energy here. It will only have kinetic energy at the bottom, and then recognize along the way that it loses the work done by friction, that friction does a negative work on it, if it has friction. But in part A, it doesn't have friction. I just say that the potential energy at the top is equal to the kinetic energy at the bottom, and that's going to be mgh equals 1/2 mv squared. The m's cancel. H is equal to 2. So that's 10 times 2 equals 1/2 v squared. So v is the square root of 40, which is 6.3 meters per second. So that's the first part. And then I have a frictional force that is equal to 2 newtons that acts all along that distance. I need to know what that distance is, by the way, so I'm going to go ahead and find that out. So 2, 5, that's the square root of 2 squared plus 5 squared. That's equal to 5.4 meters. So for part B, I'm going to say I start with the potential energy. I know what that is. That's mgh, where h is equal to 2. I deduct the work done by friction, and then what's left will be the kinetic energy at the bottom. So potential energy at the top, kinetic energy at the bottom. So that's mgh minus the frictional force times that distance, which I found that distance up there. That's equal to 1/2 mv squared. I can't get rid of the masses here because there's not a mass in every term. Some of you did that. So that's 5 times 10 times 2 minus the frictional force, which is 2 newtons. This is 2 meters. This is 2 newtons. Times the distance, which is 5.4. and that's equal to 1/2 of 5 kilograms, that's the mass, times v squared. I solved that for v. So that's 50, 100 minus 10.8. I just call it minus 11 is equal to 2.5 v squared. And if I solve that for v, I get v equals 6 meters per second. Right? Which makes sense because it is a speed that's slower, so you expect the frictional force to slow it down some. You have a collision, the total momentum, and I want to know first what is the total momentum of the system. Since I know both speeds, velocities of the particles here, I can find the total momentum. The total momentum will equal to P1 plus P2. That's going to be M1 V1 initial plus M2 V2 initial, which is going to be 1 times positive 3 plus 2 times plus 3 times negative 2. And so that total momentum is 3 minus 6, or negative 3 kilogram meters per second. Then I want to know what is the final velocity and give the magnitude and direction. So I'm going to set that total momentum, that negative 3 kilogram meters per second, equal to the momentum here. That's going to be 1 kilogram times V1F plus 3 kilograms times the final speed, which is plus 1 meter per second. And then I solve that for V1F. What is that? Negative 6 meters per second. That means it's going to be going 6 meters per second to the left. All right, this girl's doing a around the world yo-yo, traveling vertical circular path. It's spinning at an angular velocity of 8 radians per second, and the radius is 1.5 meters, and the mass is 0.1 kilograms. 0.10 kilograms. What is centripetal acceleration? With a centripetal acceleration, I'm going to call this AC, is either v squared over r, but I don't know v, but since I know omega, that's just omega squared r, so that's 8.0 squared times r, 1.5, that's 64 plus 32 is 96. 96 meters per second squared. That's the centripetal acceleration. And notice at the top of the trajectory that centripetal acceleration, AC, is towards the center of the circle. Now, the second part, I want to know the tension in the string. At the top, that is, when the string is like this, I have two forces acting down. I have the tension, and I have the weight. There's the string right there. The tension and the weight. And I know that the sum of the forces in the y direction is equal to m times the centripetal acceleration, which I just found at 96 meters per second squared. So I say that negative Ft minus Fw is equal to m times AC. And I'm trying to find Ft. So I have a negative Ft. Fw is, let's see, the mass is 0.10, so that's just going to be 1 Newton is equal to 0.1 times the 96 meters per second squared. Now you got to be really careful here with your signs because this centripetal acceleration is in the negative direction, so I have to have a negative right there. Okay, so if I find that, I get Ft is equal to 8.6, negative 8.6 newtons. Okay, I would have accepted positive 8.6. You could have also said Ft plus Fw equals MAC. If you counted this as a, oh no, I really want negative 8.6. I want negative 8.6. All right, let's look at these multiple choice. Throw a ball with a mass of 2 kilograms in the air with a speed of 5 meters per second. What is the maximum height? All right, so I throw it up in the air. I want to know to what height does it go if it has a speed of 5 meters per second down here. So I say kinetic energy at the bottom equals the potential energy at the top, and I solve for H. M's cancel. Uh, H is equal to, what's that, 12.5 over 10, or 1.3 meters. All right, this block has a mass of 4 kilograms, and it's traveling with a velocity equal to 10 meters per second. It encounters a rough patch here over a distance of 20 meters before it has a velocity equal to 0. So in short, the work done by the frictional force that's acting along this rough patch takes away all the energy that this block has. So I can say that the kinetic energy, 1/2 mv squared, is equal to the work that's done by friction, or 1/2 4 kilograms times 10 meters per second squared is equal to the work done by friction. Now, actually, I'm looking for the coefficient of friction here. So I know that F is equal to mu times the normal force. That's equal to mu, and the normal force, well, if the weight here is equal to 40 newtons, that means the normal force, because this is on a horizontal surface with no other vertical forces, is also 40 newtons. So I know that the frictional force is equal to that, and I also know that this work is equal to the frictional force times the distance. So I get mu times 40 newtons times the distance, which is 20 meters, and then I can solve that for mu. And I get that mu is equal to 0.25. So this pendulum oscillates back and forth. What type of energy does the bob have at position C? Up here, the velocity is equal to 0, so it has no kinetic energy. And the height is, well, this height, h, so it has only potential energy. All right, 2 paths lead to the top of a hill. One path goes back and forth. The other goes up, just straight up. How much potential energy would you gain if you took the longer path? Well, the change in height is the same for both, so the change in potential energy is also the same. Okay, so here I have a spring. I compress it, and it expands and causes this block to move. When the spring is compressed, it has an elastic potential energy. When it expands, it has no elastic potential energy because x is equal to 0, and the only energy that it has is kinetic energy. All right, so I know then that the elastic potential energy is equal to the kinetic energy. That's just by the conservation of energy. All of this energy goes into that energy. And I want to know the speed of the block. So this is 1/2 kx squared equals 1/2 mv squared. Now I recognize that I don't have the spring constant. However, I'll do this over here. I know that F is equal to kx. That's Hooke's law. If I am applying a force of 20 newtons um, in order to compress that spring, and I get a compression of 0.5 meters, that means that K is equal to 40. Right, so I can now solve this at 40 times 0.5 squared is equal to the mass, which is 4 times v squared. That's 10 divided by 4 is 2.5. The square root of 2.5. Yeah, so the answer is 1.6. All right, I want to know what is the total work done on this block. This force does no work, and this force does no work. Now this force, only the x component, that will be 6 um, cosine of 30 does work. And so the total work then is going to be equal to that 6 cosine of 30, that's the x component, times the distance, which is 2 meters, minus 2 newtons times 2 meters. That's this force. It does negative work because it's in the opposite direction. And that's equal to 6.4. All right, 10 kilograms kid comes down a slide. It's 3 meters high and 5 meters long. Let's draw a picture. There's a kid up there. Has a frictional force equal to 10 newtons. Acts on the entire length of the slide. How fast is the kid going when it reaches the bottom? We basically did this problem in the free response. Same, very similar. Um, I have the at the top he has only potential energy, at the bottom only kinetic energy, and along the way he loses the work done by friction. So that's mgh minus the work done by friction, that's F times d, is equal to 1/2 mv squared. I need the mass here because they don't cancel out. 10 kilograms times 10 meters per second squared times the height, which is 3, minus 10 newtons times 5 meters equals 1/2 of 10 times v squared. 10 is the mass of the kid. And v then is equal to square root of 50, which is equal to 7. Pick a bag of groceries. What can you say about the work done by the gravitational force? All right, here's my groceries right here. I'm picking them up. I'm applying a force in this direction, and the gravitational force is in that direction, but my displacement is in the upward direction. So this is opposite, so it does negative work. What is the SI unit for work? Well, work is equal to F times D. F is MA, so that's kilogram meters per second squared times meters, so it's A. All right, this is a collision problem. I start with a momentum equal to 0. That means that the final momentum will also be 0. Our PI equals PF. 0 equals, well, the momentum of this cannonball, I'll call that P1, and then the momentum of the car, I'll call this P car and P ball. It's going to be equal to P ball plus P of the car. That's 0 equals 10 times negative 100. That's the mass of the cannonball, the speed of the cannonball, plus 1,000 times the final for that car. 10 times 100, that's 1,000. So 1,000 equals 1,000 VF. So VF equals 1. And it is 1 meter per second to the right. Two objects have the same mass. One is stationary. The other is traveling at a speed v. These both have mass m. Then they stick together. Now they're going to have a mass 2m. And so what is the speed now? Well, because I'm doubling the mass, I'm doubling this value, so I have to have this value. So D is the right answer for number 11. That it will have that that speed. It'll have half the speed. All right, object mass 3 kilograms. I want to know what is the force. This looks like a change in momentum problem, a impulse problem, delta P over delta T. Because see, I have everything to find delta P. That's M delta V over delta T. Oh, I'm sorry. That's going to be 3 times 14 minus 12. It's final minus initial. over 2 gives me 3 newtons. D for 12. Softball hits you on the thigh. Which of these affects the force of the softball in parts 2? Just remind you it's F is delta P over delta T. The duration of time. Okay, yeah, that's important, right? Like if this is small, the force is big. The change in velocity, yeah, this is M delta V over delta T, so that's important. And then the initial speed of the ball, which is related to the change in velocity, so it looks like E is the right answer. All right, which of these statements is true about this uranium nucleus? This is directly from the concept test. The lighter fragment has a greater speed than the heavier fragment. Yeah, they have the same momentum. Those momenta are the same, but because momentum is mass times velocity, since the mass of one is small, then its velocity is big. So A is right, but let's just look at these others. No, that's not right. They have the same momentum, or the same but opposite, same magnitude. Uh, Likewise, same. And they don't have the same speed because they have different masses, so they have the same momentum but different speeds. If momentum of an object is tripled, how does its kinetic energy change? And assume the mass of the object has changed. So remember, momentum is m times v. So if this is tripled, that means that the speed has to have been tripled if the mass is constant. And so the kinetic energy is 1/2 mv squared. And so if this is tripled, that means I get a factor of 9 there. All right, 3 revolutions per second in radians per second. All right, kids swinging a 2 kilogram stone in a horizontal circle. This is sort of like a free response, but it's easier because you don't have to consider multiple forces. I only have the tension in the string that's acting as a centripetal force. Previously, when it was vertical, the weight and the tension were acting as the centripetal forces. Here, I can find that tension because I know that that tension is acting as the centripetal force, r, since I'm giving that angular velocity, I can say m omega squared r, and I just want to find that tension. So the mass is 2 kilograms, omega is 2 radians per second squared, and the radius is 2 meters. 2 times 4 times 2 is equal to 16. All right, theta is equal to 12 revolutions. Alpha, I don't know. I know that the time is equal to 2 seconds, and I want to know what is omega final equal to. Well, I know that omega equals omega naught plus alpha t, and I know omega naught is 0 plus alpha times t, which is 2 seconds, but I don't know alpha, so I need to find alpha. If I can do that, I'll do that up here. I know that theta equals omega naught t plus 1/2 alpha t squared, and then omega naught 0, so that goes away. So this is 12 revolutions equals 1/2 of alpha times 2 squared. So alpha is equal to 6. Did I do that right? 12 divided by 2. Yeah, 6 radians per second squared. Oh, this is not radians, actually. This is revolutions per second squared. But it doesn't matter because the units are all consistent. So I get 0 plus 6 times 2. That's equal to 12 radians per second. Excuse me, I did that wrong. Revolutions per second. Okay, this was straight from the concept test too. If an object has an angular velocity of omega in time t, what is its angular velocity in 2t? And also it's initially at rest. I know this is true. This is 0, so it goes away. So omega equals alpha times t. If I double my time, I double my omega. So C is the right answer for number 19. And then finally, if fan is spinning and slowing down, which of these statements is correct? Well, omega, because it's going clockwise, omega is negative. So that gets rid of those two. And then because it's slowing down, alpha is opposite omega. So if omega is negative, alpha is positive. So it means C.